Hey everyone, it's Miss Orpin here. I'm going to go ahead and do out a few examples that we did not cover in class so that you've got more to look at when you're trying out your homework. If you take a moment and look at A, you will see that we are taking the cube root of 125, y to the 6th power. And right off the top of my head, I look at that as two separate parts that I'm trying to cube root, and I will write them as so. Because I am multiplying 125 and y to the 6th power, each one can have its own radical symbol with a cube root. I look on the list that we had from class of perfect cube roots, and when I look at the list, I see that 125 is on there, and I also look and see that 3 goes into 6 twice, which would imply that I end up having y to the 2nd power left over. So as my final answer, I would just write it as 5y squared. You don't need the dot in between, it's a little redundant. Looking at example B, you can see I'm taking the 4th root of that fraction. And like we had practiced with numbers before, I don't know what x to the 4th divided by y to the 8th really is. So I can give the numerator and the denominator its own radical symbol. And when I go ahead and do that, I can look then at how 4 goes into 4, which would be rewritten as 4 to the 4th power. Or pardon me, x to the 4 over 4th power. The denominator, 4 goes into 8 twice, or you could rewrite it as the power over the root, which would give you a y squared. That one up top gives you just an x to the 1st. So when I go ahead and combine those two ideas back together, I get my final result of x over y squared. Moving on to C, I look at this as I have 16 times x to the 5th times y to the 6th times z to the 3rd, all underneath the cube root symbol. I'm going to first focus on my 16 and pull that aside so that I can try and break apart 16 using the cube root. And I know based on my list that 16 is not in my perfect cubes, so what I'm going to go ahead and do is look at my list and recognize that 16 does have 8 as a factor and 2. And 8 is on that list of perfects. And if I go ahead and utilize my properties from before, I can give each one its own cube root symbol, ultimately ending up with 2 cube roots of 2. However, that's not my final answer. That's just my final answer for the numeric portion. So I still have to work with my x to the 5th, y to the 6th, z to the 3rd. And like we did before, I'm going to look at how many times does 3 go into 5. Well, 3 goes into 5 once. So I will have 1x come out, and I would still have a 2nd power underneath my cube root sign. Because remember, this would be the same thing as saying the fraction x to the power of 5/3, and 5/3 can be rewritten as x to the 1 2/3. Well, here I have one whole entire number coming out, and I still have my root of 3 and my power of 2. So here's my root of 3 and my power of 2. If I move on to the y, 3 goes into 6, or y 6 over 3, be y squared. And then if I look at z, 3 goes into 3, or in other words, z to the 3 over 3 would just be a 1. There's no fractions left over. So now I went ahead and I took my variable components and broke them apart. I have my numeric components broken apart. I need to go ahead and take those two concepts and put them back together. And I look and see what's outside of my radical symbol. And I have the 2 for my numeric portion. And I have x, y squared, z. And I have my radical portion with my cube root. And under my cube root, I still have the 2 from the numeric portion, and I still have x squared from my variable portion. As long as this looks, this is considered as simplified as it gets, because underneath my radical symbol, there are no more perfect cubes. When I look at D here, I can take each one of these and no longer group them together because I have a cube root and a 4th root. So what I could do instead is utilize my properties that I do know. And instead of radical notation, I can rewrite them in exponential notation. And using the other property on front where I can subtract powers, so the numerator power subtracted by the denominator power, and actually 6/4 can be rewritten as 3/2. If I subtract those, I end up with x to the 1/6, and 1/6 can be rewritten as x to the power of 1 6th root. So there's my final answer for that one. And our last two examples from the indicated operations. I look here and I see one term plus another term. And when I analyze those two terms further, I can see that their root portions are identical. They're both an index of 3, and underneath the radical symbol there's the y. And if I look at it, I have 5 of these things plus 6 of these things. And altogether that would give me 11 of these things. And that's as basic as it gets. When I look at B, I see one term plus a second term. And when I focus in on those terms a little bit more, I notice that they both have a y to the 1/3 and an x as well to the first power. The two things I have in the purple circles are identical to each other. I have 2 of the identical circles and 3 of the other identical circles. And so when I put those together, it would give me 5 of those things that are in my circles. You could take and rewrite this then as 5x to the, that would be a root, cube root of y to the first power. And that would do it for the rest of the notes. Hopefully you found that helpful. Let me know.